So let's get started. Today we have Bruce Veenhuis from the Weather Prediction Center, who will be presenting to us on WPC's probabilistic winter precipitation forecasts and the methodologies that they utilize to produce their suite of information. So let me pass it over to you, Bruce. Take it away.
Okay. Thanks, Jeff. So as Jeff mentioned, first off, does my voice sound okay?
Yeah, we can hear you okay, Bruce.
Okay, great. So as Jeff mentioned, I'll be talking about our probabilistic winter precipitation forecast, or PWPS products. I'll start with just giving an overview of our winter weather desk operation. So our goal is to provide guidance for accumulating snowfall and ice for days 1, 2, and 3. We try to make this a collaborative forecast process, both internally between our winter weather desks and QPS desks, as well as externally between WPC and WFOs. Now, our forecasters are responsible for creating 3 24-hour accumulations for snow and ice, and from these accumulation grids, numerous products are automatically derived. This includes 6, 12, 48, and 72-hour accumulations, downscaled guidance, which is generated using PRISM, as well as our full suite of probabilistic precipitation forecasts. So the forecast process begins when our winter weather and QPF forecasters coordinate the QPF for the upcoming forecast period. Once they've coordinated the amount of QPF, our winter weather forecaster then runs a blender to generate 3 24-hour accumulations. And when they run this blender, they'll use 100% of the WPC QPF as the driver for the QPF amount. But they are free to blend different models based on their preferred precipitation type choices. And then these precipitation type choices will ultimately determine the fraction of QPF that falls as liquid, snow, or ice at each grid point. And once the forecaster runs this blender, that output will generate 3 24-hour accumulations, which they then adjust to make their final forecast. And finally, once they are happy with these 24-hour accumulations, they will launch a set of product generation scripts which automatically derive a whole variety of other products from these 24-hour accumulations. To determine the precipitation type, we rely on 2 different algorithms. For those models provided by NCEP, those models include precipitation type as an output parameter, and this precipitation type is based on the NCEP dominant precip algorithm. And the way this algorithm works is it examines the thermal profile of each grid point in the model and then applies an ensemble of precipitation type algorithms to that grid point. And finally, the most common precipitation type is selected as a dominant precip type for that grid point. For those models which are not run by NCEP, we use our own in-house algorithm to derive the precipitation type. This algorithm is just based on the surface temperature as well as the temperature at a few standard height levels. To determine our snow-to-liquid ratios, or SLRs, we rely heavily on the Rover artificial neural network technique. And this technique primarily keys on the thermal profile to try to predict a environment-based snow-to-liquid ratio. So the snow ratio we actually use is actually a blend of 5 different algorithms. We apply the Rover technique to the GFS. We also apply the Rover technique to the NAM, but then modify the SLR based on the NAM rhyme factor. We also use a climatological value, which has again been modified based on the NAM rhyme factor. And then we also use just a simple climatology as well as a straight 11-to-1 ratio. So our final SLR is an average of these 5 different techniques. And this approach allows us to compute a unique SLR for each grid point and forecast projection based on the environment predicted by the model. New for this upcoming season, we're including a dynamic ice-to-liquid ratio, or ILR, in our computations. And this ice-liquid ratio is based on the freezing rain accumulation model, or FRAM, developed by Chris Sanders and Brian Vargenbruch. And this will replace the static ice-liquid ratio we've used in past seasons. At a high level, the FRAM is a set of regression equations that relate environmental predictors to the expected ice-liquid ratio. However, for this upcoming season, we're just going to use a simplified version of the FRAM which only keys on precipitation rate. So if I draw your attention to the figure on the bottom left, this shows how the ice-liquid ratio varies as a function of precip rate. And you can see that the highest ice-liquid ratios are expected at the low precip rates, which that simply means the ice is much more efficient at accumulating when the precipitation rate is low. In contrast, when the precipitation rate increases, the ice-liquid ratio decreases. And that's mainly due to enhanced runoff, since the precipitation is falling at a heavier rate and is not able to freeze onto surfaces. So this is a new addition for this season that we're excited about evaluating the impact of this new algorithm. So just to summarize, this is how we arrive at our total snowfall and ice accumulation. First, just to start off with a few definitions. So here, the QPF is WPC QPF. A fraction of snow, sleet, or ice are those fractional precip amounts predicted by the blender choices. The SLR is that average snow-liquid ratio, and the ILR is the Fram-based precipitation rate ice-liquid ratio. So to arrive at our snowfall amounts, we simply multiply the QPF by the fraction of precipitation determined to be snow, multiplied by that average snow-liquid ratio. To determine the portion falling as sleet, we simply multiply the QPF by the fraction determined to be sleet, multiplied by a static 2-to-1 sleet to liquid ratio, and then we finally just sum the snow and the sleet to arrive at the total snowfall. To compute our ice accumulation grids, we multiply the QPF by the fraction of precipitation determined to be ice, multiplied by that Fram-predicted ice-liquid ratio. As I mentioned, we also apply prism downscaling to our accumulation grids, and this technique allows us to add fine-scale detail to our grids in areas with complex terrain. So you can see on the left panel here, this is an example of a non-downscaled 24-hour snowfall forecast, where the figure on the right is showing the effect of the prism downscaling. And you can see that this technique does enhance the accumulation over areas of complex terrain. So now that I've given an overview just of how we arrive at our deterministic grids, I'll talk a bit about some important about the timeline for our day shift and night shift. The first important timeline for our day shift, which is responsible for preparing the 0Z issuance of our products, occurs around 18Z. This is when the forecaster will post the preliminary guidance and notify WFOs via AWIPS chat that the guidance has been sent. We also say that this marks the beginning of the official collaboration window. However, we would like to stress that collaboration does not have to be limited just to this collaboration window. Collaboration can actually occur at any time throughout the forecast process. Around 20Z, our forecaster will make any final edits to the snowfall and ice accumulation grids based on any feedback they receive from WFOs and any results of collaboration. They'll then send the final guidance and launch the final product generation scripts. The following 0Z time marks the beginning of our day one guidance valid period. And an important point to note here on this slide, as these times are just our internal deadlines for preparing our products. The actual arrival times at WFOs will be a bit later, and I'll touch on that in a couple slides. Here's the same information except for the night shift. Our night shift is responsible for preparing the 12Z cycle. These times are similar to the day shift except shifted by 12 hours. So as I mentioned, there is some difference between when we launch our final product generation scripts and when these grids should actually arrive at WFOs. Again, our winter weather forecaster will notify WFOs via AWIPS chat when products have been sent. For the day shift, which is responsible for preparing the 0Z guidance, WFOs should expect to receive our preliminary guidance between 18 and 1840 UTV, and the final guidance between 20 and 2040 UTV. For the night shift, which is responsible for preparing the 12Z issuance, the preliminary guidance should be available around between 6 and 640 UTV, and the final between 8 and 840 UTV. The reason there is this this approximate 40-minute window in the time WFOs will receive the grids is that there is some day-to-day variation in the time our forecasters actually send the products. We also have to allow some time for the products to be generated and sent over the satellite broadcast network or through the LBN. And I tried to depict a worst-case scenario with these time ranges. So, for example, with the preliminary 0Z guidance, 1840 is probably the latest this guidance should ever arrive at WFOs. So everything I've discussed so far simply explains how we create our deterministic snow and ice forecast. But you recall an important aspect of these product hours is that they also include probabilistic information. And to create this probabilistic guidance, we combine our deterministic forecast with information from our so-called PWPF ensemble. That allows us to create probabilistic guidance, which we can share with WFOs, who can then use that information to communicate the expected accumulation. Here's an overview of our PWPF ensemble. This is a multi-model ensemble composed of the members shown here. One thing to note is there are 70 members in total, and this includes the WPC deterministic forecast. I've just highlighted a few changes for the upcoming season in bold. For this season, we are going to use 10 guest members randomly selected rather than the 5 we used in seasons past. We're also including the WRF NMMB and WRF ARW as additional ensemble members. However, since these models arrived fairly late and are only run to 48 hours, they will only influence the day one portion of our forecast. So to maintain a consistent number of ensemble members across all projections, we're actually substituting the 0Z or 6Z GFS for days 2 and 3.
Excuse me, this is Cleveland. Do you know the resolution of these members? Is that available somewhere?
It varies depending on model, but like information, I can make that available. It varies depending on which model source.
Okay, thank you.
We do internally, everything is, for processing purposes, everything is processed on a 20-kilometer grid, but then we do downscale that to 2.5 kilometers. So this is how we use the information from this ensemble to generate our probabilistic forecast. So to actually do that, we start by examining the distribution of the ensemble members, and recall that this ensemble now includes the WPC deterministic forecast as an additional member. So in the figure here, shows our snowfall accumulation plotted along the x-axis and the probability plotted along the y-axis. The green curve gives a sense of the ensemble member distribution. And the WPC forecast is highlighted by the red star. We use a statistical technique that shifts the mode of the distribution so that the mode becomes equal to the WPC deterministic forecast, but the spread of the distribution is equal to the spread of the original ensemble. So this allows us to place greater emphasis on the WPC forecast but still acknowledge the uncertainty information in the ensemble. So now that we've created a probability distribution, that allows us to communicate the uncertainty information to WFOs. And there's a couple of ways we communicate that information. We produce so-called probability of exceedance grids. These simply provide the probability that an accumulation will exceed a certain threshold. So, for example, if the probability of receiving more than 4 inches was, say, 40%, if you had a ruler, that would simply mean there's a 40% chance that the accumulation will be greater than 4 inches. And conversely, a 60% chance that the accumulation will be below 4 inches. We also create so-called CDF percentiles. These provide a single value which shows a certain probability of not exceeding. So, for example, if the 90th percentile was equal to 6 inches, that would mean there's a 90% chance that the observed accumulation will be below 6 inches and conversely, a 10% chance that the accumulation will be above 6 inches. So that gives an overview of how we create our probabilistic guidance information. I'd now like to touch on just a few frequently asked questions. First off, a very common question is, do WPC's forecast accumulations equal the 50th percentile of the distribution? The answer here is no, not necessarily. Recall that we set the mode of the distribution equal to the WPC forecast, but we do allow the distribution to be skewed either to the left or to the right, so that the mode does not necessarily have to equal the 50th percentile. In the example shown here, the top left map depicts our 50th percentile accumulation. If I call your attention to the area near Duluth, Minnesota, you can see that the max is around 6 inches. The figure on the right shows our deterministic forecast. Here you can see that the maximum grid value is actually around 9 inches. So in this case, our deterministic forecast is actually higher than the 50th percentile. So if you were to examine the distribution at this point, it would probably be skewed to the left. Another common question is, does WPC's deterministic forecast influence the probabilities? The answer here is, of course, yes. Recall that we adjust the distribution of the original ensemble members such that the mode or most common value becomes equal to the deterministic forecast, with the spread equal to that of the original ensemble. So this, again, allows us to place greater emphasis on the deterministic forecast while still acknowledging the forecast uncertainty. Finally, another very common question is, how are these probabilistic forecasts verified? Well, verifying snowfall and ice accumulations is always challenging. There's two primary data sources we rely on for verification. The first, we use 24-hour point-based accumulations provided by the co-op network. There's also a grid and snow analysis available from the National Operational Hydrologic Remote Sensing Center, or NORISC. However, some deficiencies were noted in this analysis during the previous winter season. There is a new version in the works. However, that is not expected until fiscal year 2017, or the second quarter of fiscal year 2017. It's also important to point out that multiple cases are required to properly judge probabilistic forecasts. Two common tools we use are attribute diagrams, which show statistical reliability. We also can compute the Breyer skill score, which provides provides a sense of how skillful our forecasts are compared to a climatological forecast. So the figure on the right here is an example of an attribute diagram. And this diagram contains a wealth of information. First off, if our forecasts were perfectly reliable, then the black dots here should all fall along the black dashed diagonal reference curve. And that would indicate that the forecasted probability matched the observed frequency. You'll note there's also a line here, a red line here, which demarcates a skill versus no skill region on the diagram. The best way to understand this line is, if you recall, the Breyer score can be decomposed into a reliability, a resolution, and uncertainty component. So this no skill line provides a sense of the balance between your resolution term and your reliability term. So if a point were to fall below the no skill line, that means that the reward for having good resolution is being outweighed by the poor reliability. And then that point would actually have a negative impact on your Breyer skill score. Here's an example of some actual verification. This is verifying our day one probability of snowfall exceeding 4 inches at co-op and against co-op sites and the no-risk analysis. The figure on the left shows our verification relative to co-op sites. You can see that our forecasts were decently reliable. There was a tendency to over-forecast. For example, if our predicted probability was around 75%, the actual event only occurred around 50% of the time. And you'll note our Breyer skill score is a positive 0.32, indicating we do have skill relative to a climatological forecast. The figure on the right is verifying our forecast against the no-risk analysis. Here you can see the story is much different. The reliability is much worse, and it's actually a negative Breyer skill score, suggesting our forecasts are worse than a climatological forecast. The large discrepancy in these results did let us to question the reliability of the no-risk analysis. And one point to make is that the version of the no-risk analysis that was operational last season only assimilated point-based observations and did not include background first guess field. So that seems that approach resulted in a rather poor analysis in areas with sparse data coverage, such as the West. So as I said, there is a new version of the no-risk analysis in the works, which will be available in 2017. On the next slide here, this verification is again for the day one probability of snowfall, this time exceeding 8 inches. The figure on the left is verifying our forecast relative to the co-op sites, while the figure on the right is verifying our forecast relative to the no-risk analysis. You can note that our reliability is worse at the higher threshold because it is a more challenging forecast. However, compared to co-op sites, our bar still score is still positive, but again, you see the same discrepancy in verification at co-op sites versus the no-risk analysis. We do face some ongoing challenges with our approach. One major challenge is accurately resolving small-scale features such as lake effect snow. The map on the top left here shows our WPC deterministic 24-hour snow forecast, while the figure on the right shows our 90th percentile 24-hour snow forecast. And you can see in this case, our deterministic forecast is very close to the 90th percentile. And the reason this will occur is many of the ensemble members in our PWPF ensemble are natively at fairly coarse resolution, which can result in too small of a spread for the high-end amounts. And here at the bottom right, you can see the actual observed max forecast was around 18 to 21 inches, whereas our 90th percentile was on the order of 15 inches. Finally, another common question is how do I access the data? The probabilistic snowfall and ice accumulation grids are sent directly to WFOs by the satellite broadcast network. This includes 24, 48, and 72-hour accumulations provided at 6-hour intervals. Our deterministic snowball and ice grids are distributed via LVM. We also make the grid 2 available at the URLs shown below. So in summary, our winter weather desk provides accumulation guidance for days 1 to 3. Again, we try to follow a collaborative forecast process. Our forecasters are responsible for creating deterministic forecast grids, but from those forecast grids, numerous products are automatically derived. And this guidance is being shared with WFOs via the LDM and SBN. Again, just to reiterate some of the key deadlines for the day shift and night shift, WFO should expect to receive our preliminary guidance between 1800 and 1840 UTZ and the final guidance between 20 and 2040 UTZ. And while the night shift guidance the preliminary guidance should be available between 6 and 640 UTZ and the final between 8 and 840. So that's all I had for today, and I'd be happy to answer any questions.